We're going to talk about the understanding fire in the Australian landscape, how they and where they occur, covering topics such as extent, mapping, prediction, severity and recovery. And our first speaker in the discussion and also the moderator of the panel discussion is Andrew Edwards. Dr. Andrew Edwards is a researcher at the Darwin Centre for Bushfire Research, Charles Darwin University. Andrew has worked in GIS and remote sensing, primarily applying these skills to fire ecology. He is involved with the North Australian Fire Information Web Portal, providing burnt area mapping and other fire information to 70% of the Australian continent, including the tropical savannas and rangelands. Andrew is part of the team of scientists and Indigenous land managers who are responsible for the development of the savanna burning methodology, which has earned project areas in North Queensland millions of dollars annually through greenhouse gas emissions abatement. Currently, Andrew is further refining savanna-wide fire severity mapping to improve the savanna burning methodology, whilst working on other projects to assist Indigenous rangers to monitor and evaluate bushfire management. So Andrew, I'll put myself on mute and hand over to you, and if you just let me know when you want to advance the slides, we'll go from there.
No worries, thank you, Sylvia. Yes, if we could just go to my first slide, there we are. So that's just showing my affiliation. I'm with a group called the Darwin Centre for Bushfire Research. We're based within the Research Institute for the Environment and Livelihoods at Charles Darwin University. We've been here for about 6 years. Prior to that, we were at Bushfires NT, which is the rural fire management agency in the Northern Territory. 20 odd years ago, we were getting requests to make maps of fire locations. So we developed this website eventually that stands in quite good stead today, called NAFI, the North Australia Fire Information website. We use active hotspots, plus we have burn area mapping that's done by a couple of my colleagues at least once a week throughout the year. And we have a lot of other fire information that's up there as well, fire metrics that are derived from the burnt area mapping history. For the last 20 years, we've been mapping using MODIS since its inception in about the year 2000. If we could go to the next slide, please, Sylvia. Thank you. Okay, so this is just a brief introduction of the webinar from me today. I'm not giving a full-blown presentation, but I just wanted to point out a few of the key data sets that are available to us either nationally or near nationally that I find of great value, and we've been using for many, many years and are used by fire managers across North Australia. What you're experiencing in Eastern Australia at the moment, as horrific as it is something that's fairly much an annual process in North Australia. We have that level of fire every year across North Australia. Something like 40% of North Australia is burnt pretty much every year. So that NAFI page there in the top left is and there's a web address there for you to go and have a look. You can have a look at the extent of the burnt areas, plus you can look at active fires. That active fire data is updated pretty much every hour as data become available. The other website that I'm always really impressed with is Firewatch, run by Landgate out of Perth in Western Australia, Western Australian government. It's fantastic. It has so much information available to it. To the user, all sorts of fire mapping at all sorts of scales, as well as hotspot information, active fire information, etc. And lots of modelling and that kind of thing goes in there as well. So you can do a lot of analysis and a lot of for planning for burning. Whereas NAFI is meant to be very over 95% of our users really just want to get on and see if they've got a fire in their area today. So they'll get on and look for the active fires, the hotspots, and if they see anything, then they'll, go into a bit more detail and look for a bit more information. In the top right there, the data portal, the Turn data portal, has tons of data. It's static. There's burn area mapping, there's fire severity mapping, stuff that we derive up here. There's a whole lot of other really fantastic products produced by the Queensland Government, the Remote Sensing Group. to do with persistent greenness and fractional cover, all these really amazing data sets that are very, very useful for planning and for land management and for mapping of all sorts of things, as well as fire. And then, of course, I know it is normally, doesn't ever need to normally be said, but we are so reliant on the BOM and their data and the currency of their data and the accuracy of it. It's, you know, they're outstanding data sets that we use all the time. So I know there are many more other websites out there, and perhaps this might be the beginning of of some sort of portal that we could develop to find all these sorts of things for other people in other parts of Australia. But you can see here there's quite a lot of information that covers a lot of the continent. The first thing I have to do next is to introduce Marta. And so Dr. Marta Yebra is a senior lecturer in environment and engineering at the Fenner School of Environment and Society and Research School of Aerospace, Mechanical and Environmental Engineering, where she's mission specialist of the ANU Institute for Space and associate editor for the Remote Sensing of Environment. Good grief, Marta, how do you have the time? Her research focuses on using remote sensing data to monitor, quantify and forecast natural resources and natural hazards with a focus on mapping bushfire risk and impact on local, regional and at global scales. From 2004 to 2010, she was employed at the University of Alcalá, where she was involved in 2 large multidisciplinary projects which assessed and integrated the main fire risk factors and analysed fire risk trends at regional and global scales. During her research, she also spent time at the University of California, Davis, at the National Institute of Agricultural Technology in Argentina, and Salford University in the United Kingdom. From 2010 to 2013, Marta was a postdoctoral fellow at CSIRO Land and Water, developing innovative remote sensing methods to predict carbon-water coupling. Marta's research has been recognised through numerous awards, including the Max Day Environmental Science Fellowship from the Australian Academy of Science in 2017, the CSIRO Pine-Scott Career Award in 2013, and the Award for Outstanding Achievement in Research Utilisation from the Bushfire and Natural Hazards CRC. So, oh, goodness me, she's obviously an amazing and wonderful scientist, and we're lucky to have her in this country. I'd like to welcome Marta to speak today. Thank you.
Thank you, Andrew. That was a long presentation. Thank you very much. It's a pleasure to be here talking to you today. And my talk will present a brief summary of the most recent developments related to the use of remote sensing in fire management. I need to acknowledge a lot of people that has been helping and supporting my research. In this slide, you can see a few names, but there are much, much more names that will appear as I present. Next slide, please. Yeah. So remote sensing data has been used in fire-related research and management since the early 70s. So the first applications were based on visual analysis of aerial photography. But after the launch of Landsat, satellite data has been used for different phases of the fire management. So before the fire, remote sensing data is used to estimate fire danger conditions mainly. So fire danger is a combination of a wide variety of topics from which weather, fuel, and human factors are the most relevant. So in this topic, remote sensing has mainly contributed to the characterization of fuel condition. So then satellite data has also been used to provide firefighting intelligence during the fire, more frequently using active fire or hotspots detection systems, as Andrew has presented a few of those. And these systems mainly are based on the use of middle and thermal infrared observations and are used to estimate the fire spread. But also remote sensing data on fuel condition has also been used to, for example, identify soft containment lines based on differences on fuel moisture content. So finally, the remote sensing data also provides important information to analyze the fire effects and vegetation recovery after the fire. And this information supports remediation activities, as we will see later. Can everyone hear me well? I see somebody's writing that you don't hear me. Well, I assume everything is good. It's okay. All right, so given the topic is very broad and we have other two presenters, my talk will mainly focus on the use of remote sensing for fuel condition characterization, and I will only briefly touch on the post-fire applications. So the objective of my talk today is to share some examples on the remote sensing information used to support current and past bushfire management activities in Australia, rather than highlight the methodologies used to derive the different products. So it's not going to be a very technical talk. So this is the next slide. So I would like to start by emphasizing that when it comes to characterizing fuel condition using remote sensing data, there is not a single source of information that fully fits the purpose. So this slide is not comprehensive, and I'm not going to go into detail, but I put it here to quickly see that each sensor may be able to detect only a specific fuel property, but also with certain limitations. So consequently, to meet the user requirements from sensors that have not been specifically designed for fire applications, scientists only have the option to combine different sensors and systems, from optical LiDAR to radar to thermal optical, to really get the full picture about the fuel condition in the landscape. So my hope in the future is that taking the advantage of the new era of small sats and better sensors, we will be able in the near future to design a mission that is specifically targeted for bushfire management. So bear in mind. Next slide, please. So why is, let's start talking about fuel conditions. So why is it important? So I pick up as an example this study from some colleagues from FENER that used fire behavior predictions to demonstrate that for houses surrounded by a given percentage of trees and shrubs, the mean probability of house loss was less when the vegetation surrounding the house had higher values of NDVI that was used as a proxy of greenness or wetness of the vegetation. So for example, the orange line, you can see that if the cover of the trees and the shrubs around the houses was 20%, and the average NDVI 0.24, then the mean probability of house loss was below 0.5. If the cover was doubled to 40%, and this is the red line, then the mean probability of the house loss increased to 0.5. However, if at the same time we increase the NDVI to 0.4, for example, by planting species that are wetter or by keeping your lawn very wet and green, then the mean probability decreased to around 0.35, despite doubling the cover of trees and shrubs. So next slide, please. So because of all this study and many others that have demonstrated the importance of fuel condition and funded by the Bushfire Natural Hazard CRC, we developed this website that is called the Australian Flammability Monitoring System that provides information about live fuel moisture content, flammability, and soil moisture content. So the live fuel moisture content maps are derived from MODIS data, and the algorithms that used is based on radiative transfer model inversion techniques. So it's a physical-based model that we have also demonstrated that is sensor agnostic. So it can be applied to any other satellite imagery that has the adequate spectral bands, of course. So in the website, we also provide what we call a flammability index. So this is an index from 0 to 1 that basically converts the fuel moisture content absolute values into a likelihood of fire occurrence. Basically, if you through a match or if there is an ignition source, how likely that fuel is going to ignite, having into account the moisture content conditions uniquely. And then in the system, we also host soil moisture content values into different depths of soil. And this data has been produced by the BOM using their Jasmine modeling system. Next slide, please. So what can we see with this information system? Here I have put some screenshots of, on the left top is the average value of fuel moisture content conditions for different fire weather areas in Australia. And for example, we can see that most of the areas are with fuel moisture content values quite low. So that's why they are all in orange and red values. There's only an area in Victoria that is pretty wetter than the rest. So the system also allows to look at the data as the size. So you can see how a given time compares with the long time series of data in 2001. And here again, we can see that most of the areas, especially in where all the fires are, and in the bottom of the slide, you can see the current incident feed that comes from the different fire agencies. So you can see that all these areas where most of the New South Wales fires are happening at the moment are not only having very low fuel moisture content values, but also moisture contents that are well below or below the average. And some areas are not average. Next slide. So how is the system then currently used? So it's intended to use, so it's been tested to use. So basically for more than perhaps we originally planning, because originally we planned to be used for planning and preparedness, but this fire season we've been also testing it for response, as I will show a few examples. So in terms of planning, this information can give you very important information to scheduling the prescribed burns. So you may know that if a fuel is too wet, a burn is never going to happen as much as one will push the mat into the fire. And if the fuel is too dry, there is a risk that prescribed or a hazard reduction burn will go out of control. And also, if because this system uses optical data, when we are in a very closed forest, the fuel moisture content values mainly come from the canopy of the trees. This also provides important information for prescribing. Yes?
Okay. Good. 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 How are you?
All good?
Yes.
Okay. All right. Then gives you an idea of how dry the canopy is, and with that, what is the potential of the canopy to be scorched when they are do prescribed burns. Preparedness and the system, this information can be used to amend the preparedness levels in relation to fire danger rating in response to lower, higher than average landscape dryness conditions. For example, if for a given day we have a high danger, the authorities may consider to raise it to severe and issue a total fire ban if the landscape is extremely dry. In terms of response, the fuel moisture content is an input in one fire behavior, but for the other fire behavior models that are currently used operationally, this spatial information on fuel moisture content cannot be directly ingested because the fire behavior models are not ready to do that. So what we are doing at the moment is to provide the information to raise a bit of awareness on the potential anomalies in the predicted rate of spread given the moisture conditions. And as I previously said, it can also give some information about where there can be soft control lines that can be used to stop the fire because the vegetation is too wet. Next slide, please. So this is, for example, an example of a map we provide to national parks on the current North Black Range Fire that is on the left of the screenshot, and the Caravan fires on the right. So, for example, this raised awareness on the condition of the fuel. We can see that the fire, the North Black Fire range, started in a forest that had moisture content conditions around 100, 120, and those values for a forest are considered quite dry because they are below the threshold values that are considered dangerous for forests. And then we also showed that the fire, the ignition point was surrounded by very, very extremely dry scrub and grassland areas. So those areas, the fires in grasslands are normally easier to fight because lower fuel loads. But if they are extremely dry, the fire may spread very, very fast. So that's something that also needs to be considered. So on the right of the screen, I show the current situation of the fires, just to show that the fires at the moment are only separated by about 20 kilometers of extremely dry grasslands and near the North Range Fire, and some very dry forest near the Caravan fires. And next, please. So remote sensing data, as I said, has also been very useful to provide information about fuel structure and load. And we've been doing a lot of research in this area, and on the left, you can see the results of some research we did using terrestrial LiDAR. With this handheld LiDAR that was developed by CSIRO, and you see a photo there of one of my past students. We were able to classify a forest very detailedly in the different layers of the forest, and with this extracting metrics on the fuel load and fuel structure. But this was not ever going to be operationally used because the fire managers, although got very excited about the accuracy of the results, found the system still very expensive to use and not feasible for their operations. So they still are more happy to use airborne LiDAR. So what we did was with the airborne LiDAR that was collected in 2015 for the whole ACT, we derived some fuel metrics for the different fuel layers on the forest. And this is, for example, the elevated fuel cover for the whole ACT. So next slide, please. So how is this being used or not used, and what has happened if it hasn't been used? So for example, this is the elevated fuel fraction of cover of an area around one of the prescribed burns they did a few autumns ago, or last autumn, I don't remember exactly when. So if you see in the map, there is a road in red that goes from the south to the north. So the firefighters, the ACT parts were using this road as the containment line, but when the fire approached this area highlighted in red in the west of the plant burn with very, very high fuel loads, the fire went out of control and jumped the containment line. So talking to Brian Levine, after this happened, he thought that if he would have looked carefully at these maps, he would have planned the burn differently or put more resources in that containment line to avoid that to go out of control and jump the line. Next, please.
Marta, just to remind you, you've just got 1 more minute, please.
Okay, thank you. So talking about fire severity, and I know the other speakers are going to cover this. So this is, for example, a map of fire severity we derived using an algorithm of one of my students using radiative transfer model inversion techniques, and Andrew is also a co-author in this paper. So the problem of this fire that was in Queensland this season is that it burned right up to 2 significant dams, and therefore they were very worried about the quality of the water, so they wanted to quickly start to do remediation efforts to protect the water supply. So next one, please. So quickly, without going into detail, there are many, many different algorithms to derive fire severity. And this is an example of 3 of the algorithms we derived and we analyzed in the Pierces Creek fire that happened last year in Canberra. And they all, for this specific fire, work similarly. But what I wanted to highlight is that they have different advantages and disadvantages. For example, the radiative transfer model-based algorithm only requires 1 single image post-fire. So that simplifies the computing. But the algorithm we developed in collaboration with Geoscience Australia it uses change detection. So it needs a long time series of Landsat imagery, but it is fully automatically, and the algorithms are available in GitHub to be used with the Digital Earth Australia. And then with my colleagues in the University of Monash, we developed another algorithm using a new spectral index that is very sensitive to fire. Okay, next slide. And next, let's skip this one. I'm running a bit late. So using this new index, we have also been able to track the index after fire and have been able to fit that to curves of fuel accumulation curves derived by Google. And this has been useful to provide information about fuel load. As you can see on the left. And this information about fuel load in combination with the fuel moisture content can give a bit of information on what areas should be targeted. So for firefighting, for example, those areas with higher fuel loads indicated with the blue arrow, together with areas that have very low fuel moisture content, might be the ones that are at more risk for the fire to spread faster. So next one, I'll leave it there with these conclusions for you to read, and if you have any questions, I'm happy to answer if we have time.
It doesn't look like we've got time, Marta. You've gone over quite a bit, but we will have a discussion at the end of the 3 presentations. So if people would like to keep their questions to that point in time, that would be great. I'd like to introduce our next speaker, please. Our next speaker is Phil McKenna. He's an ecologist and research scholar at the Centre for Mined Land Rehabilitation in the University of Queensland. Phil completed his master's thesis in 2018, assessing the fire behaviour, severity and recovery of a controlled burn in central Queensland using ground surveys and a combination of WorldView 3 and drone imagery. He's now managing a research project across Queensland assessing the resilience and response of rehabilitated land following multiple fires, and is using predominantly planet and drone imagery to measure fire severity and vegetation response at a local scale. Combined with ground surveys, the research outcomes will be used to increase our understanding of fire impacts and improve rehabilitation outcomes for mine closure, which I'm sure you can all agree is quite important. Phil originally studied forest science at Melbourne University before moving to Queensland in 2007 to work with the Centre for Mined Land Rehabilitation as a field ecologist and GIS specialist. He has been chief investigator on a number of research projects in Australia and overseas. He's developed and implemented long-term monitoring programs on mine site rehabilitation at more than 10 mines, providing specialist advice on matters such as vegetation and ecosystem development and legislative compliance. With no further ado, I'd like to introduce Phil, who's going to be talking about mapping fire severity.
Thanks, Andrew. Welcome, everybody. Thanks for having me along. Today I'm going to present some of my project work from my PhD, which is looking at mapping fire severity using planet and drone imagery. And this work is focused on measuring the resilience of mine site rehabilitation, but it's also, I think, applicable to the impact that fire has on the resilience of many ecosystems that are burnt. Next slide, thanks. So today I'll give you a brief introduction to the concept of fire severity, a little bit of the history and some of the common indices that are used. And I'll present two case studies from my work on one at North Stradbroke Island and one in central Queensland. Next slide, thanks. So in terms of definitions of fire severity, I'm using that defined by Keeley in 2009, which is the loss or change in organic matter above ground and below ground. And it's particularly important, I think, to differentiate between fire intensity and fire severity, because there has been some used interchangeably over the years. So fire intensity is the energy released during the fire itself, normally expressed in kilowatts per metre. And fire severity or burn severity is the loss of biomass from the system or the organic matter loss. Next slide, thanks. So the history of fire severity mapping really dominated by the early Landsat sensors. Initially, the Landsat was used for fire perimeter mapping, but then a number of studies after that showed the potential for characterising a range of fire impacts. And since then, there's been many sensors that have used, there's actually many hundreds of studies that demonstrate comparable map accuracies when mapping fire severity. Next slide. And many of these studies use indices such as these, so NDVI and normalised burn ratio, and they really exploit the spectral changes that are occurring in the near infrared and the shortwave infrared parts of the electromagnetic spectrum. We use image differencing typically. We have a pre-fire and a post-fire image, and using those equations we can create an image that represents absolute change in terms of severity. Next slide. And this is an example of a workflow that I've used to create a severity map. I've circled a couple of key points there. Top right, there's a number of corrections, geometric, radiometric, atmospheric, pseudo-invariant features that need to be applied to the imagery before calculating the indices and the severity map to improve accuracy. And in the bottom left, something I think is very important was field severity surveys used to calibrate and validate the map. So without ground surveys, we really have no way of knowing how representative some of the changes we have in our severity map, how representative they are of what's on the ground. I'm going to talk a little bit about that section, that box there. It says fire severity map thresholding. So if we can go to the next slide. And this is taken from the 2006 document published by the US Forest Service. It provides a guideline really for some of the thresholds used to separate the classes of severity using normalised burn ratio. But I just wanted to point out the caveat at the bottom there, which reads that value changes are flexible, they're scene pair dependent, and shifts in thresholds plus or minus points are possible. So it really indicates, I think, how important field mapping is, because then we can set our own thresholds based on the calibration points that we've measured on the ground, and align that with the type of sensor we're using and the spatial resolution. Next slide, thanks. And when we're ranking severity on the ground, we can use a number of methods, and this is an example of one that I've used recently, modified by a paper from Schaefer in 2004. I quite like this method because it's rapid, but ranking fire severity in the field can be a challenge, particularly getting your eye in. It does help if you have other observers that you can calibrate with. And when you get into the higher severity rankings, it really becomes about the remaining fine fuel that's in either the mid-story or on the trees themselves. There's been a number of studies that have correlated remaining branch tip diameters with fire severity classes. And there's a number of other ways to measure fire severity as well on the ground. So composite burn index is one used commonly in the US. And it's different for different ecosystems. So for example, in grasslands, you might be more interested in focusing on the remaining grass stub lengths rather than trying to find canopy impacts. Next slide, thanks. And this is the first case study at North Stradbroke Island. I'm in Jerrabah, and I use those ground severity rankings at this site. So this is using planet imagery. And you can see, so planet imagery is 3-metre resolution captured daily. You can see on the left-hand side there is the pre-fire image and the NDVI down the bottom. The next column across is the post-fire image and the NDVI post-fire. You can see the fire scar there, which is represented by the darker pixels. And the next column across is my validation points. We captured 188 points on the ground. And then the NDVI map down the bottom there shows the areas after the differencing, the areas of high severity of the white pixels, the higher pixel values. And then the fire severity map on the bottom right-hand corner shows areas of very high, and low to moderate. This map was actually used by the traditional owners who have sites of significance in the swamp just on the western side of that burn. It's also that burnt a patch of rehabilitation as well. So the rehab manager is using this map to plan his replanting and rehabilitation efforts. Next slide, thanks. And this map was, as I mentioned, validated with 188 points. This is the error matrix, which measures the agreement between the ground reference points and also the difference NDVI values from the severity map. The circle there shows that an overall map accuracy of 76%, which is reasonable. And error matrices are good because you can break it down into individual classes and see the commission and emission error for the mapping process. Next slide, thanks. And just to provide context, so that previous fire, that fire that I was just talking about burnt in September this year, that was nearly 600 hectares. But this fire was 2013 fire and this is burnt nearly 60% of the island. So this is nearly 16,000 hectares. And here I used Landsat 8 imagery and normalised burn ratio to map fire severity. And you can see that the centre part of the island burnt at a much higher severity compared to the rest. Next slide. Moving on to the second case study now, and this is at a coal mine in central Queensland. This is actually a controlled burn, and we were able to instrument this fire and get some fire behaviour metrics. Next slide, thanks. There's a couple of photos just to give you an idea of the fire. So it was a night burn, so it was a very cool, low fire danger conditions. It was in the end of the dry season. Next slide. And we had the QFES fire behaviour guys with us to help assess fire behaviour. Next slide. We used these thermochrons and they're about the size of a $2 coin. So they're little temperature sensors. We buried them about 1 centimetre below the soil and at each of our plot corners. So we have 6 plots on this site, 50 metres by 10 metres. And yeah, so we were able to accurately measure the time that the fire moved across our plots. And so we're able to calculate rate of spread and also infer fire direction. Next slide. And because we measured biomass and a detached litter on each of these transects, pre and post fire, we're able to calculate fire line intensity to quite a detailed level. And you can see that of the 6 transects on the right-hand side there, one in particular, transect number 4, burnt at a very high severity. And that transect was burnt with a frontal fire with the wind behind it, whereas the other transects were all burnt with side fires or backing fires. Next slide.
Phil, you've got 3 minutes.
Thank you. And this shows the transect change over time for that particular one that was burnt at that severity. Note at 6 months post-fire how green that vegetation has become. Next slide. And putting that into context, I've got a time series of planet NDVI imagery, and I've plotted that out against daily rainfall. You can see how closely linked the NDVI is to the daily rainfall. You can also see how the burnt site, so this is averages for the whole burnt polygon versus averages for the control polygon. And you can see how the burnt NDVI drops significantly below the unburnt and then responds to rainfall. Next slide. And this is mirrored by other metrics on the ground, such as plant species richness, which are also closely aligned to daily rainfall. Next slide. So moving on to the drone, so for this site, we used MicroSense Red Edge. So it's a 5-band sensor, and we captured it with a DJI Matrice 210, and we processed it in Pix4D. So we've got 4 mosaics in these time series, and we're capturing another one next year for the 2-year post-fire assessment. Next slide. And there's a number of advantages to the drone imagery. So the high spatial and temporal resolution. This is 10 centimetre imagery, so you can see individual canopy impacts and fine ash patterns in the burnt site. You can also see individual changes in one particular species of shrub at this site, which is present in the pre-fire image, and by the post-fire, by the 12 months post-fire, it's actually almost completely died out. Next slide. And this is the fire severity map that we use from the drone imagery. It's a variation of the NDVI, so we use green-red NDVI, and we got an overall map accuracy of 74%. Next slide. And this shows, yeah, the index is able to pick up some of those deaths of that particular shrub once you threshold at the extreme level. You can see on the severity map those round areas of dark red which represent those shrubs, and also some of the high combustion areas in the site. Next slide. And this shows on the ground one of our transects. Those arrows are pointing to the start of the transect. And there's a number of limitations with drone imagery that are quite specific to drone imagery. So one of those is the shadowing effect from canopies, which can introduce heterogeneity into the fire severity map, which are not represented on the ground. There's other specific photogrammetry errors, so convoluted canopies, where canopies appear quite cloudy, and also radial displacement of some of the tall trees. Next slide. So just in summary, the planet and drone imagery is suitable for severity and recovery mapping. The scale of the fire is really going to determine which sensor you use and which is appropriate. I didn't mention this, but something that's exciting about severity mapping is the automation of severity mapping using a range of script options. And just the accuracy is an issue without validation points. Severity rankings may be ecosystem specific, and when you're using drone imagery, there's a number of limitations that you need to be aware of for this final severity maps. Thank you. Next slide.
Oh, that's great. Is that you, Phil, finished?
Yes, that's me. Thanks, Andrew.
Oh, well done. Very good presentation. Thank you very much. As I said, we'll have questions and discussions at the end of the 3 presentations. Our third and final presenter is Dr. Leonardo Hardtucker. He works at the Joint Remote Sensing Research Program at the University of Queensland in the School of Earth and Environmental Sciences, where he joined them in 2018. He's a spatial ecologist. He graduated from the Universidad Nacional de Comahue in Argentina. His interest in wildfires started early in his career, studying the ecological role of fire and its interactions with the environment and the economic activities in Patagonia in Argentina. In his current role, his main research priority has been to develop and operationalise a method to map fires from Sentinel-2 imagery across Queensland. And we've been lucky enough to have some of his work given to us to use in the Northern Territory as well. Thank you, Leo and colleagues. With no further ado, I'd like to introduce Leo, and he's going to talk about operational fire extent mapping.
Hi all, thanks Andrew for the introduction. Yeah, I want to show you what I've been working for the past year or so. I hope you all can hear me well. Well, in a nutshell, it's a system that enables us to have frequent maps of burnt area across all Queensland at a high spatial resolution. Next slide, please. So as we all already know, a large area of Queensland burns every year, and we need to know precisely when and where it burns, because that has, okay, I can start my video. Sorry about that. Can you see me now? Okay, I hope you can see me. Probably now. Okay, I was not prepared for a video, but here I am. Okay, so as I was saying, we know that Queensland burns every year a high percentage of it, particularly up in the north, and that has implications on the vegetation structure, biodiversity conservation, landscape condition, carbon emissions, water and air quality, and wildfire risk management. Next slide, please. So what's the information we currently have available to answer those, describe those dynamics? Those are hotspots like MODIS that are available through the NAFI webpage and the Sentinel webpage that have very good temporal resolution, but are not good enough to map the actual fire extent. Then we have the MODIS 250 meters burnt area maps provided by NAFI as well, that have a very good temporal coverage, but don't quite enough have the spatial resolution to show the patchiness of the fires. And then we also have Landsat-based burnt area map that was developed here in the Department of Environmental Sciences of the Queensland Government by Nick Godwin and Lisa Collett, and they produced a long time series map of burnt areas from 1987 to 2017. Next slide, please. That method worked really well, but it's very expensive to run in our system, and it can be only updated once a year, and it was usually available by June of the next year. So next slide, please. So we needed something a little bit more inexpensive to run and with a similar accuracy and a good spatial resolution. So next slide, please. I'll give you a little bit of background. So we all know in the remote sensing community that burnt areas show a decline in the near infrared and an increase in the shortwave infrared, which is what the normalized burn ratio, which is the most used index, uses. But while developing the Landsat method that I mentioned previously, it was noted that here in Queensland, the response really varies across the environment, and it was not the best index to use. So they actually ended up using a different thing. I don't remember exactly which one it was, but basically the NBR was not good enough for us. So I decided to go a little bit a different way and use a more physically based, sorry about the camera, a more physically based index, which is the using a fractional cover layer. For those that are not familiar with fractional cover is a product that gives you the proportion of bare soil, green vegetation, and dry vegetation for each pixel. And as we know, fire consumes biomass, which of course will increase the bare soil fraction. And we use that principle to map fires. Next slide, please. So here in this image, you can see how this is up in North Queensland. You can see on the left there, I think that's a Landsat reflectance, and on the left, and then on the right you have the bare soil fraction difference between two images, and you can see clearly the red areas, which are recently burned areas. Next slide, please. So basically, we use that knowledge to develop our algorithm, which is basically a change detection between a rolling cloud-free reference image that I keep and the last image that comes into our system. The workflow can be summarized in 3 steps. First, we use the temporal difference of bare soil fraction to identify potentially burned pixels. Then we use a regional growing segmentation algorithm to actually grow that area and find the extent of the area. And then we use decision trees to discriminate between burned and unburned areas, because the second step still yields a lot of false positives. Next slide, please. So to actually optimize the thresholds and fit the decision trees, I used manually edited fire polygons for 2016. I used 13 scenes to cover all the variation in Queensland environments and 9 dates to actually sample across the fire season as well, which ended up being 145,000 points. Next slide, please. I forgot to mention that this method doesn't only work on Sentinel, it also works on Landsat because it requires only the fractional cover and reflectance, and we have them both for Landsat and for Sentinel. We just decided to go with a method that works Sentinel alone because it's cheaper to run and it has an overpass of 5 days. So in this plot, you can see the different change index I tested. It's on the left is the index that Nick and Lisa used for this Landsat time series approach. Then on the right, there's the DNVR, and in the middle is the difference in bare soil fraction. And as you can see, the one that worked best, so it has the less overlap between fires and non-fires, was the difference in bare soil fraction. So that's the index we used for our method. Next slide, please. So we used that threshold to separate fires from non-fires, but there's still some overlap, and that overlap is resolved by the decision trees later. So next slide, please. I'll show you now a short sequence of a fire that happened up in the north last year. And this just show you how the system works, and I may highlight some features. So please allow 2 seconds per image in the sequence, and then if I ask you to stop to show you something, please stop it. So start the sequence. So you can see the date up in the left, and as the sequence advances, you can see how it basically maps the fires. Stop in this one, please. So one of the features, and something that confuses some people when they look at the image, is that it has some holes, and those holes are usually because to make the system work good for all Queensland. It has very high, very restricted thresholds on the cloud and shadow thresholds. So some of the very bright areas on the front of the fire are confused with clouds, and some very dark soil or very highly separate burnt area is confused with shadows. So it has those holes that you can see maybe in the center of the fire there, but they are usually mapped the next time when they are not so bright or so dark anymore. So please continue on with the sequence. So yeah, so you can see how it maps the fire and how it really follows the very detailed the perimeter of the fire. So we, of course, did some validation exercises. The first one was by the end of last year. We manually edited the polygons for 4 months of data for the Southeast Queensland. I think we evaluated 11 scenes, and we got a precision of 87% and a recall of 85%, which yielded an F1 score of 0.66, which made us very happy. Next slide, please. And then we made a more Queensland-wide validation exercise, selecting 24 scenes for 4 dates and dropping 5,000 random points per image. And we got a precision of 93%, a recall of 87%, and a F score of 0.91. Which definitely made us very happy. So next slide, please. Of course, the method has its validation, its limitations. Sometimes, especially up in the north, there are some long periods without cloud-free images. And when you have your next cloud-free image, the signal of the fire already disappeared. So you will miss that fire. And also the index is a little bit not so sensitive on very high canopy cover areas, and it gets confused with smoke. That's for the omission errors. And for the commission errors, we still have some problems with the cloud and shadow masks. Some areas of high change also get confused, especially cropping areas, and some areas of inundations also get confused in the system. Next, please. And for the current status, we applied this method to all our archive, which are 245 tiles, which makes more than 63,700 individual images. And we are trialing weekly, monthly, and yearly unedited mosaics. We are planning to start editing the outputs soon and make them available through Turn and NAFI web pages. So that's my presentation. Thanks all.
Wonderful. Thank you, Leonardo. That was a wonderful presentation. Very, very fantastic results. I'd like to open the floor to people. There's a number of methods whereby you could ask a question. You could either type it into the chat and I can read it out, or you can put your hand up in the participants list. There's a little button there at the bottom left that says raise hand. If I see a raised hand, I'll call your name and you can ask a question through the audio yourself. I'd like to start by asking you, Leo, about how you think the method that you've developed might be now applicable to fire severity mapping. You've obviously got pretty high accuracies through the automated process, and you're going to improve that accuracy obviously much more by manually editing. What do you think, or how have you got work or knowledge about the fire severity process that you might be?
Yeah, definitely fire severity is our next goal with the fire program. I've been working a little bit in teaming up with people from New South Wales. They have a lot of training data that I like, so I don't have any field data at all. We've been trialing it, and it seems to be basically it's not yet working good because the thresholds are definitely are dependent on the environment, and we need to have our own training data to make it work properly. So yeah, we need to work on that.
Oh, that's great. That's really great. There's a couple of questions being put up here for Marta. Are you online, Marta?
Yes, I am.
Okay, I don't know if you've seen this question, but I'll read it out for the audience anyway. It says here, is the burn severity and fuel load condition map available online?
No, not yet. So these products are still under development together with the University of Monash and a student we co-supervise, that is Andrea Massetti. But yeah, the idea is that once these maps are fully developed and fully validated with field observations, we will hopefully make it available through the Australian Flammability Monitoring System as well.
Okay, and now we have a question for Phil. Are you there, Phil?
Yep, I'm here.
The question seems to be quite general, but it asks, how do you calculate fire intensity?
Yep, so fire intensity is the amount of fuel that's being combusted, multiplied by the rate of spread and multiplied by a fuel constant. So it's a pretty simple equation, but you need to have a fairly accurate understanding of how fast the fire is moving and also how much fuel is being combusted.
Fantastic, good answer, thank you. I've got a question here for Leo. It's obviously very timely and pertinent. Have you and are you making fire maps for the current fires in New South Wales and Southern Queensland?
I'm not preparing maps for New South Wales. I'm just producing the automated output for Queensland, which includes the Southeast Queensland. And we could, I could try producing some for New South Wales to see how well it does. I really don't know because I never tried. And yeah, something to keep in mind is that Sentinel has a 5 days overpass period. Mm-hmm. And sometimes there is cloudy or smoky, so we can look through the clouds and the smoke. So sometimes you have to wait until 5 or 10 days after the fire occurs to have the actual extent of the fire, the full extent of the fire. If you're lucky, you can get it the next day, but usually it's not the case. Usually, to be realistic, you have to wait about 10 days or 15 days to get the extent of a particular fire.
Yeah, right.
Thanks for the question, James.
Anybody else with a question? I haven't seen anything else come up.
I've got a question from South Australia.
Go for it.
Just a general question is, which is better for burnt area mapping? Is it the normalised burn ratio index or the fractional burn cover algorithm? Is there any particular one that's better or worse depending on what the application is? We're probably looking at it more from an extent mapping point of view. Just curious to know from the floor what their opinions are.
I think it's going to be very sensor dependent. I mean, it depends on the scale you're working at. So, I mean, if you wanted maps updated regularly, you'd have to move to something that's acquiring data regularly. If you've got large areas to map, then you want to move to something that produces data at much larger areas, like the MODIS satellite data. And I think Leo can probably talk at that sort of Landsat Sentinel level about the differences in accuracy.
So sorry, I was a little bit distracted with it.
I was just wondering, have you made a comparison in the accuracy of mapping using the standard indices like the normalized burn ratio compared to your fractional bare ground.
Yeah, definitely.
algorithm.
We tried that. It was kind of the first step on my work, and we found that NBR works better than the fractional coverage.
I wouldn't mind to comment on that.
Oh, okay.
That's all right. So we did, Andrea Massetti, our student, did a bit of a comparison of using NBR and this new algorithm, for example, based on this new index. And in terms of total fire extent, the results were very similar. But what we show is that his index, for example, was more sensitive to fuel recovery. So whereas other existing index didn't have any burn extent in an image a few months after the fire, these index were more sensitive to the fuel recovery. But in terms of total burn extent, they were similar.
Okay. Yeah, I think our work has shown something
I like
along the same lines.
what
Most
I
of those
was
indices are fairly similar. Sorry, who's speaking?
No, that we found the fractional cover index to be more general than the NBR. The NBR worked better in some places, but really didn't perform well at all in some others. So that's why we ended up using the fractional cover one. It was just more general. Yeah, sorry about that.
Can I jump in there, Andrew?
Please do.
What I'd say is really depends on the ecosystem you're looking at as well. So the normalized burn ratio is really developed in forested ecosystems, and for example, NDVI and normalized burn ratio are really measuring different things. So the NDVI, the near infrared part of the spectrum, is really measuring, it's correlated with biomass, but it's also measuring light that's scattering off cell walls. Whereas the use of shortwave infrared, even though it's proportional to biomass, it's very related to the amount of water content in the leaves. So if you're trying to measure severity on a grassland, for example, and grasslands, as we know, burn when they're very highly cured. There's really no moisture in that vegetation. The normalized burn ratio really breaks down in environments like that. And that's when things like NDVI will really work much better than normalized burn ratio.
Okay, Phil, you might be able to then carry that on to this question that Chris Tom has asked. How can you then calculate burn severity in uniform fuels such as spinifex grasslands or heathlands? What's your thoughts on that?
Well, I mean, it depends on which sensor you're using and how big the fire is. I think the size of the fire will really have a big determination on what sensor you're using, because you can calculate NDVI from any of the sensors. But if it's a big fire in spinifex, then drone imagery is not applicable, and Planet is a bit harder to work with. And you're really looking up into the Sentinel or Landsat, much more sort of spatial coarser scale. But yeah, grasslands, I've found that NDVI works better than other indices like normalized burn ratio. One of the things with the NDVI though is it's very sensitive to soil background colours. So if you've got different coloured soils, it can have an impact on how well the NDVI works. And so with the drone imagery on the central Queensland side, I actually got a better result using the green-red normalized NDVI. So, and I think it gave me a histogram which was much broader and much more spread out, and I could develop thresholds that were a bit more accurate, I think. And it really adding the green and red together for that NDVI equation, I think, enabled the change in the spectral values between the pre and post fire image to really stand out a bit more.
Great. Yeah. Sorry, I had a question here. It disappeared. Yeah, somebody else uses Sentinel-2 too. Yeah, I think I've got a question for you, Phil, about just carrying on the notion of using drone imagery. I had a colleague up here who tried to use drone imagery, and he found a lot of trouble getting the photos to match because the eucalypts just sort of disappeared. They were moving in the wind, being so light, and so because the leaves of a rectified, you know, they're drooping, the trees just disappeared from the matching. During the image, did you find anything like that with species?
Yeah.
Any specific species that you can?
Well, on my study sites, I've got a range of eucalypts and acacia species, and the acacia is definitely much easier to pick up just because the canopies are much more dense and they don't move as much in the wind. Yeah, eucalypts are notorious for trying to capture with the drone imagery because it initially captures, it ties down points that are matching between images and creates a point cloud. And if between images the leaves or the canopy is moving, then it just cannot find those tie points. And that goes back to some of the clouded, convoluted type canopy images that I was talking about in my presentation. So there is, even though drone imagery is able to capture, you know, you've got your high spatial and temporal resolution, there are a lot of limitations that are really specific to drone imagery when you're trying to even create a mosaic, right? Let alone look at two different time sequences to do image differencing with. So you can introduce a lot of heterogeneity that's not present on the ground.
Excuse me, Andrew, I think the question that you missed was the one by Matt Garthwaite, which was, has anyone investigated the use of Sentinel-1 SAR in-SAR data for the burn mapping application?
Yep, that was my next question. Have any of you, the presenters, got anything? I presume, Marta, you might have something to say about SAR, having used LiDAR. Are you there?
Well, we haven't used it directly, and from the top of my head, I don't have any specific study that has used it for burn area mapping.
Yeah, right. I have seen people try to use it in a tropical savanna setting, and without very much success. If Renee was online, she might have something to say about that. I think that was work she did in her thesis many years ago. Is she there, Beat? Was she going to talk about the Earth observation?
I'm here.
Ah, do you want to talk about, you weren't here before when you were introduced to talk about the forum next year, Renee. Would you like to say something about it?
I'll wait till all these questions are all answered and Sylvia can introduce it.
Cool. Do you want to say something about SAR data for mapping fire, please, Renee?
Yeah, so we used it successfully. We wrote a paper maybe over 10 years ago. I can't remember what the outcomes were because it was so long ago, but I'm happy to, I can look it up quickly and put a link to it in the chat if people would like.
That'd be cool. Yeah, because there's very little being done, and what has been done has not been very successful. But I remember you had some success. And what do you attribute the success to, Renee? Do you recall? Was it like extensive amounts of ground truthing?
There was very little ground truthing, I think. Yeah, so, but...
oh, so
yeah.
you just made it up. Is that
No, we didn't just make it up. I honestly can't recall the details. It was that long ago.
All right, we'll just wait for your link then and make our minds up from there. It just seems there was a couple of questions about SAR, using SAR data, you know, because of its ability to penetrate cloud. Yeah, but it's not been, I've never seen it applied successfully anywhere with burnt area mapping. All right, any more questions? Oh no, Nick has raised his hand. Nick, where are you?
Yep. I've got another question from South Australia. Maybe to Leo. Is there any direction to operationalise that and make it more workflowed in with you know, data set generation for your jurisdiction? And are there challenges to do that?
So we are working to make it operational for Queensland and very likely for the Northern Territory. We don't have the capacity to run it nationwide from here, but more than happy to share our method and try to implement it somewhere else. Definitely contact me if you are interested.
Yeah, I can do that. Sure. Thanks.
That's great.
Excuse me again, Andrew. There was a question from TDC. How about using hyperspectral to develop and confirm fly mapping satellite products?
In terms of TDC, are you online?
Yes.
Oh, yes,
I'm
you
here.
are. You've got some audio. So
Yeah.
what are you talking about with the question? You're talking about an intercomparison to sort of, in a sense, validate data mapping, or you're talking about collecting calibration data?
Well, some of the work, we go back, you know, at least 10 years in this sort of area, using airborne hyperspectral to, you know, image post-burn areas, and some excellent work. I don't know if people can see it, but I put a JPEG up where we went from classifying using, you know, hyperspectral data, the products that are sitting on the ground, whether they're ash or partly burnt vegetation, etc., and then converting that to a burn severity map, which worked pretty well because we compared it with, for that particular fire, which goes back to 2001, to a map prepared by Sydney Water of the same area, and like the correspondence when you see the two overlaid is, you know, like very, very good. So Sydney Water used pre and post satellite imagery, and we just did some classification, as you see in the top there, of what's on the ground from the spectra. This is some excellent work done by Bissendat at the time. But then when you convert it into a severity map, there's a, you know, very, very good match. And yeah, and you know, the idea is that using the hyperspectral, you're actually classifying what's on the ground, you know, uniquely through the spectral identification. It's not some, you know, magic ratio or something that you try to do. And as I said, like, this is done more than a decade ago.
Yeah.
And
so how much do you reckon that cost then?
Well, that data you're looking at was free because we did it as a test flight, pre something else. I'm not suggesting that you use hyperspectral to map, you know, on a basis anything near what you might do from a satellite. But if you wanted to start developing algorithms, you know, this is with the hyperspectral, you got all the bands, high resolution, high spatial resolution, and then you scale your algorithms from that up to your satellite, whatever's got the satellite. But in a way, the hyperspectral gives you ground truth.
No, that's great. I think you'll find that a lot of the indices that have been developed, or the band combinations, do come from that sort of application, that sort of algorithm development. So yeah, it's a really good thing you pointed out. But and I think that's what many of us do. I think that's where a lot of the algorithms have come from, using hyperspectral data. Thank you. What's this as a comment here? Is that from Renee? Oh, here it is. We used TopSAR and found that the shorter wavelength was more appropriate than the longer wavelengths. Excellent, thank you, Renee. I think we're nearly close to time, are we not, Sylvia? Hello? No. Oh, Nick, you've got your hand up again, have you? Or is that from last time?
I think it's stuck on permanently. I'm going to turn it off. Sorry. One more question. Is there any intent to have any more of these webinars? Because they're quite useful from my perspective. What's anyone's thoughts on that?
I'm just the moderator. I don't have any control.
Okay.
Where's Sylvia? She or Larissa? Or Joe?
Okay, I will. I've got my mic on and I'm ready, so I'll go. Yes, is the short answer. We are probably going to be over the next couple of months working on themes and ideas for themes for next year. So we're happy to hear feedback from the community and suggestions, which you can email directly to us at admin@eoa.org.au, and I'll probably put a notice up on the website to that effect as well, but there will be more information coming out over the next couple of months up on the website. So we'll be planning on running the webinars. I think it's once every 2 months. Yeah.
Okay.
Sorry about that, everyone. I somehow lost my internet. Apologies.
No worries. I'm glad you're back.
I can't seem to get my screen though. Bear with me a moment.
Okay. No worries. So, Kevin Harding, you've got your hand up. Did you have a question?
Yeah, sorry. Kevin Harding here. I'm a forester, also sit on the board of Institute of Foresters and Australian Forest Growers, so representing both forest managers and growers. I'd just be curious for a comment from all of you as to what's the sort of uptake, routine uptake of this sort of technology now by the rural fire services and others out there. It would seem that perhaps we're not hammering enough the fact that we've got this sort of technology available to do the sort of pre-planning for an obviously very bad fire season this year, and not much better than last year, or no, sorry, even worse than last year, but which was a bad one as well. So I'd be interested just to know if there is sort of uptake. You know, Phil's maps of the mining area, you know, the green after 6 months, but then everything looked pretty dry by about August this year. Well, I mean, did the managers there then implement a fire coming into this fire season just to knock that back down, which would be an obvious, just simple application of it?
Phil, are you there? Did you want to respond to that question?
Yeah, thanks,
to that
Kevin.
point, part of the question?
Yep. You can imagine, Kevin, getting coal miners to burn something is a little bit tricky. So they definitely, after that fire, didn't want to go in and reburn again. That part of central Queensland is dominated by a particular invasive grass called buffel grass, and that's really highly invasive with high fuel loads. So the mine managers are really interested in the work that I'm doing. They're interested in what it means for them in terms of risk for them, because many of the mines are actually certifying some of the rehabilitation, which means that they're preparing to sign the land back to either traditional owners or the government. So they're very interested in the work that I'm doing. They do use the maps. I mentioned in my presentation that over on Stradbroke Island, the mine managers there have used my maps for planning their restoration efforts, and also the traditional owners are using the maps. I've found, because I've started, I communicate fairly regularly with the QFES fire modelling guys, and they're very supportive of some of the work that I'm doing, and yeah, they're really interested in it. So, but in terms of a broad uptake across a statewide or a national scale, I think some of the other presenters might have some other comments.
I look from the North Australian perspective. The NAFI web service had 9 million map requests this year. So I think there's a fair bit of uptake in the north where we've got a lot of fire, and I imagine other areas with similar services would be being hit pretty hard in the same way. I know my sister lives in Sydney. I was watching fires near me on an hourly basis for most of last week. So I think there's plenty of uptake of the information. And
well, that's great to hear. The other one that struck me was the bare soil mapping there, because I'm up in far north Queensland, and that's probably entirely relevant to the whole land management thing to minimise sediment flows into the river systems here and out to the reef. So, you know, that's pretty crucial work to be incorporated into management and timing of burns, etc.
Yeah, no, good point. Yeah, that's so you've got the Turn data portal, which I think I threw up an address for on this, but you can just search on that, and they've got that great fractional cover data that you can use to look at the fraction of bare ground, the fraction of photosynthetic and non-photosynthetic vegetation for any point at about a 30 metre scale. I think it's 30 metre Landsat data, so it's a pretty incredible data set that's available for your purposes.
It's 30 meters Landsat, and there is a Sentinel as well available there. So any questions about that, just contact me and I can point you to the right place to get the data.
Right. All right. Any more hands up? Okay. No more hands up. I think we're pretty much out of time, unless anybody's got a real burning question. I think we might wrap up for the day. Thank you.